Oh, I had f of b minus f of a. So I did that guy, and then I plugged in x, and then I did minus, and then plugging in 0 is the same thing as f prime of 0. I just shortened the process. Sorry. Did that turn out what you guys got? So then f. Nope. Sorry, I'm going back. I did so I plugged in x, and I plugged in 0, but plugging in hold on, that's confusing. Shouldn't be minus 4, it should be plus 4. Where's my logic messed up? It should be plus 4. Yeah, it'd be 0. I see. In my head, it makes sense. Why is not making sense here? Because the antiderivative of f double prime of t antiderivative minus f prime of went away, it took it away. I don't want to do that. Okay, yeah, it is 0. But what it equals over here is f prime of x. Would add the f prime of 0. Yeah, that makes more sense. Sorry. There we go. That's the accumulator function using FTC, which we haven't actually talked about yet. But you could have also had plus c, and then you could in your go back again. This wouldn't be f of x. This would be f of x minus f of 0. There. I think because we have to go back to f, right? There we go. And that'd be t cubed over 3. And that'd be 12 squared over 2. That'd be 4t from 0 to x. F of 0 is equal to negative 5, right? So f of x is going to equal x cubed plus 6x squared plus 4x minus 5. Which is the same thing you guys should have gotten if you had done plus c and plugged in. Or I guess maybe that would be plus c, that would be plus d. Either way. Yeah, you could. Technically, in their perspective, I don't think they had done indefinite integrals yet. Have you guys done indefinite integrals with plus c? I don't think so. Yeah, so you would have to use the FTC idea from going from an initial to x. Go team. Oh, but that's because of antiderivatives from last chapter.
Yeah, I know.
It introduced antiderivatives with the idea of plus c with MVT, right? It introduced antiderivatives, but you didn't see an integral sign, did you? I think it just said antiderivative. Oh, got it. Well, it did say antiderivative. We talked about it briefly in class. But you guys see totally why I don't teach AB with this textbook, right? Like, letter B. Oh, that was just plugging in. How are you guys on numbers 1, 2, and 3? Are we okay?
I don't get 2.
Have you guys thought about doing a right Riemann sum of what I say is the answer using n equals 20 rectangles? Think about it. A right Riemann sum of what I say is the answer using 20 rectangles. Does it match up with what you see? Check me. Check.
Why is it square root x over 20? Yeah.
It's not.
No, but on...
Take the interval 0 to 1. You have to cut it into 20 subintervals. You're going to have to go by 1/20ths. Think about it. Going from 0 to 1, n equals 20, you're going to have to section that up into 20ths. 1/20th, 2/20th, 3/20th, 4/20th. What are you plugging in for your heights? 1/20th, 2/20th, 3/20th, 4/20th. Keep thinking. Sorry, I'm still solving. What are we doing? Of f? Oh, of this guy. Ugh. Do you guys stick it to the man hardcore? So be x to the 4th over 4. That'd be 1/4. That's f of minus f of a. Yes, box it and be done. You guys can experience it. That'd be 1/4. Hey, wait a minute. Oh no, he's not a function. We almost could have just gone and called him 0. It doesn't work. That would have been fun though. Negative 1 to the 4th plus 2 times negative 1 cubed. Minus 5 times negative 1. I think I legally put all my grouping symbols. You guys realize if you messed up a grouping symbol, they would take off a point, right? But we got it. That's all f of b. We got it. Because if you miss a grouping symbol, like for instance, if I missed this one, actually that one would probably be okay. But if I missed like this one, then it would mess up the distribution technically. Struggle, right? And my f of b, and then my 1/2. Okay. Whoop. So what's, oh, Justin, for up here?
Can you explain like number 2 graphically? I don't understand why there's like...
Oh. Let's go over here. They said it was a Riemann sum approximation. So right away, I actually looked here to figure out my bases, right? Because it's going to be base times height 1 plus height 2. I knew that there were 20. There were 20, so there were 20 different rectangles being used. And I saw that my b sub b minus a over n, I was like, oh, hey, that must be 1 minus 0 over 20. Now, could it have been something else? Yes. But I just assumed it was what I saw, and then I checked if it worked. So I assumed it was 1 minus 0 over 20. Could have been maybe 5 minus 4 or 3 minus. But then I saw starting at 1/20th, so I thought of a number line. And I was like, 20 over 20 is 1, which ends where I assumed my interval was, from 1 to 0, 0 to 1. Ends at, but then it starts at 1/20th. Wait, well that's 1 removed from, oh, it must be a right Riemann sum. It must be a right Riemann sum, starting at 1/20th, ending at 20 over 20, going through each of my That made sense with my n equaling 20, my interval being 1 minus 0. And then all I had to do was say, well, what's all of these 20ths being plugged into? Oh, square root of x. Dun, 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 dun. The hard thing is they didn't tell me what n was. If they had told you what n was, it would have made it a lot easier, because then you would have known that you were splitting some interval into 20ths, and you could have looked and seen, oh, hey, what's underneath the... Now, if you guys looked at all the rest of them, just imagine. If you split 0 to 1, you would have had to split 0 to 1 somehow, right? What if you had just done 1? Well, if you had just done 1, there only would have been 1 base times height. There are 20 different rectangles, so this interval would have had to get split into 20ths. So then you would have had 1/20th, 2/20th, 3/20th being plugged in, and over another 20. These should have been 400ths. This would have been even worse. This would have been 1 over 20 cubed when you tried to plug in your 20 different. So the number of rectangles gave me a huge clue in. And all of these needed to get split into 20ths. Now this is one that was interesting because this one goes, sorry, I zoomed out too much. Is that 20? This one's interesting. Because this one, if I was to split 0 to 20 into 20ths, that would be going by ones, right? Oh, but going by ones wouldn't make sense with my base. So the only one that makes sense, splitting into 20ths and having my base being 1/20th, is only this one. Splitting 0 to 1 into 20ths, that gets me the base. And then needing 20 different rectangles, plugging in each of my 20th along the way, only works with this function. Does that kind of help? Okay. Guys, can you still get... Let me put it this way. Can you guys still get tricked by basic ideas being tested or questioned weirdly according to the AP style? Yeah. Like, these are basic Riemann sums, but that's a hard question. Yeah? How many of you guys got B without even looking at mine? See what I mean? We can do this, but it makes sense why we still need to master some concepts, yeah? To that end, I really want to do that one, but I'm not going to because we already did one the other day. We did not get to do this yesterday, but technically, have we taken notes this year on antiderivative? Pause. Have we taken notes on antiderivatives? We did in chapter 5. As Riley pointed out, there was an antiderivative on the test. Why? Because in MBT, we introduced the idea of antiderivative. So do you need to write this again? I don't think so. You have it as a forever card. We wrote it down in chapter 5. Could you write it again? I suppose. What I'm more curious about is, are we okay? Or why on earth did I think you were okay skipping these 2 examples and just going and doing homework? What's the antiderivative of e to the x? And how do we solve definite integrals? F of b minus f of a. Does that make sense, though? So we get e minus 1. Yeah. 6-3 was due today. Was it on Google Classroom? Oh, spoiled rotten. Yeah, I guess we'll correct it tomorrow then. Oh, we can go play in section 6-4 today and not get behind. Okay. Are we okay with x cubed? Whoa, how'd I get x cubed? I added 1 and I divided by x to the n. The integral is x to the n plus 1 over n plus 1. From negative 1 to 2. What, Mag? I still didn't hear it, but I pretended. So, why? Why was it not a big deal? Because we're okay on antiderivatives, right, guys? Okay. So, 6.3, okay, fine, due tomorrow. Party poopers. 6.4 isn't due till Thursday anyway, so maybe I was giving it a little extra grace. I don't know what was going on with that. Maybe I just... Wait, to that end, I really want to do that. No, we should do this instead. We'll save the other one. I wanted to race you guys and actually race, not let you get started and then go over to the boards and write out all my work, but we'll do that another day as an opener. I know. I was excited. Section 4, we did AP practice, which is good, and you guys got stuck on number 2, which is also good. Because Riemann sums are enough to make almost anyone humble in calculus. Oh, they're not that bad. We just might not have totally mastered them as well as we thought we did. But that's okay. Oh, I meant last year. Because this year's the master year. Last year wasn't the master year. Some of you might have felt like it was the master year. Some of you did get a higher level of mastery than some. But I think BC is really where you start developing your mental math capabilities in calculus, which I see as some sort of level of mastery, right? If you can do it in your head. I have a kiddo in Calc 2 right now, out at Moore Park. Is that where she is? Got a 3 on the AP back in her day, barely. An AB. She's doing crazy U sub integration by parts in her head now. It's crazy. It's crazy cool. Still makes little mistakes on the silly stuff. Algebra 1 wasn't her forte. But it was pretty cool. I've tried to, I don't know. Like, I'll meet up with coffee. But. Huh? You want me to zoom in? Sorry. 8x. Yeah. Depends on whether you're going semesters or quarters. For undergrad, like non-engineering, you usually go Calc 1, 2, and 3 if you're on semester schedule. So there's 3 different sections. If you're on quarter schedule, there's 4 different sections. Quarters are funny because quarters, they still want you to have a full year of something, but there's now 4 classes. So sometimes with quarters, you get to take things faster, and sometimes it's the exact same amount of time, which is ironic in my head. But anyway, things like calculus, they split it up differently in quarters. They spread it into 4 classes as opposed to 3. So CalcBC on a semester schedule is similar to Calc 2, but we don't go over, the main application we don't go over is work. There's some things with like springs and other stuff too, but work is a main application that is not tested on the BC exam. I wouldn't be surprised if it eventually was because professors probably are mad that we're not covering it. But work is a main application that we're not covering with integration, which has its own formulas and it's more physics-y stuff. Think the motion, but like a whole different application, sort of. And then some college professors go into proofs more, especially if they're like a pure mathematician. They're going to use the calculus as an impetus or as a lead-in to a lot of the higher proving. So like at Cal Poly Honors Program, their Calc 2 is a whole nother level than our Calc 2 because it wasn't about can you do it, it was about can you do it and show why this whole thing is true anyway. Like, it's a whole different approach. So it kind of just depends on where you are and what the point is of their program and what they're trying to do with the class. So, but it's similar to Calc 2. But I would advise for any of you guys, even after you ace the BC exam, to probably, if you do need to take more calculus, I would go into Calc 2. Because you're solid, you're going to have seen the sequences and series, you're going to have seen the integration by parts and harder integrals, you're going to have seen the main things. You're going to be introduced to a few new things. It's a nice, easy transition. It's a nice, easy transition. That would have been the 3rd level. So yeah, CalcBC doesn't go into Calc 3 at all. And he could have, yeah. Surprised he only needed 1 more.
Yeah.
Engineering in grad school usually goes Calc 4, Calc 5. I thought undergrad, maybe not.
I think because he went to, because he was at CC for 1 year
Yeah.
before he transferred.
So maybe he did something
I
there.
think he like finished that. And so I'm guessing like that was kind of like his just like his GE.
Like his undergrad GE level. That makes sense. They probably have 4 engineering. Okay. Yeah. Because then they start making it all particular to what they're doing. And the pure mathematicians get hard and say, well, they're just playing. They're not learning how it pure and applied kind of fun. It's okay. Everybody judges everywhere you are. The question is, what are you doing? What's this? It's not an X, it's a U. What's this? It's not an X, it's a U. What could we do? Couldn't we take the derivative of both sides? Right? If g of x is equal to, they love to do this. They love to name the accumulator function as something else. If g is, you killing me. If g of x is equal to the integral from a to u of f of x dx, if I derive both sides, what happens? Yeah, but how does it not become an integral? Who is the antiderivative? And who is the integrand of f?
U. F is U.
U is the bound. A is f is the integrand. I apologize. What's the antiderivative of f, though? Okay, we could do that. So then capital F, but you would plug in b and then a, right? True? Okay, so if we were to try to solve the integral from a to u of a function f of x dx, it'd be antiderivative of u minus antiderivative of a. True? What happens if you take the derivative of the antiderivative of u minus the antiderivative of a? It's yeah, we could call it f prime of u minus 0. What did I forget? I can go to that, but I'm forgetting. I think someone's saying it, just doing it quietly. Derivative of the inside. You killed a bunny! The whole point of using a u is that it's not an x, right? So the derivative of the antiderivative of u is the derivative of the antiderivative, which is the original, of u, of u times u prime. Wait, why is the derivative of the antiderivative of a just 0? Yeah, I'm just reminding you guys, because this one only goes to x, this one's going to u. Last year I wrote down this stuff, but you had no understanding or concept of the idea until we went through the chapter, went through the test, etc. So now I'm hoping that you fully understand why the answer is what it is. Maybe a few of you did, but not many. Yeah. So integrating f, I get antiderivative of x from b to a. So antiderivative of b minus antiderivative of a. Derivative of this guy, whatever, f prime of u times u prime, chain rule, minus, if we were to do this, prime of a, but who's a? Just a constant. So then if you didn't realize that's just a constant whose derivative is 0, when you go to do a prime, hopefully it will hit you then. So derivative of any constant is just 0, which is why the rule says the integral from a constant to a variable, specifically an expression, will always be, still f of, but it's f of u, and it needs always a u prime. Well, just thinking about the AP, just specifically for you guys as far as what's coming. Don't they love to let another function equal the accumulator function in FRQs? They love it. And then they ask you all kinds of questions about it. So what if they ask you when g is increasing? You have to get a derivative of that guy, otherwise you're not going to be able to answer it, right? Or if they ask about where g is concave up or concave down, or where g is speeding up, or slowing down, you're going to need to take all sorts of derivatives. Now, once you get the first one, it's not a big deal to take the second one, right? But they're going to force your hand in order to answer increasing, decreasing, speeding up, slowing down, concave up, concave down. I don't know. They can put it different ways, but in order to answer that, you're going to have to be able to derive. So, as far as that specific application for right now. So what would you guys do? Some of you are like, easy cheesy, perfect, let's go. So in answer to Maggie's question, why might they be asking me this? Did you guys notice how just a second ago I set up quite a couple, well no, it was only 2, I was going to say quite a few. I set up a couple integrals like this from 2. What was I doing? In the multiple choice? No, I'm sorry, in the FRQ from the back of our homework spiral. Why was I making integrals where I started at 0 and went to x? I was using FTC, but what was I doing? Why did I make an integral from 0 to x anyway? You guys all did plus c. I was trying to make an expression for the original without using the plus c and with using an initial condition. So you could think of this as an initial condition. You could think of this as an accumulator, as in we don't want to end it. It has to be in terms of t so that doesn't match. looking at the derivative. Anyway, just giving you a peek behind the scenes as to where this might have come from. Can I read this? Thank goodness they're asking for the... Okay, nice. So since it's from an a to an x, that's as simple as what? But who is my u? Nope, making it too hard. If I'm taking if I'm trying to find d dx, I'm just taking d dx at both sides. It's FTC part 2. Who's my u? Just x.
Yeah, me too.
Why?
Because I thought u was square root 1 plus e to the 5t. Isn't it just...
If we were integrating by hand, but do we need to integrate? The whole point of the fundamental theorem of calculus is if you're deriving an integral, aren't they inverse operations of each other? So without having to do any of the integration by hand, we can think of, well, whatever his antiderivative is going to have an x plugged in, minus is going to have a negative 2 plugged in, and come right back here. F times u prime, just one. What were you guys doing? That's so illegal, whatever it was he was doing.
I did like that.
Oh, you plugged in and then you did him prime?
Yeah, no, I did him, and then I did 1/2, like that, the negative power.
Stop. Wrong.
And then I did e to the 5t.
Wrong. Okay, so, hold on, pause. Hold on, pause. We want dy dx again. This is why we want dy dx. We could call this, if we wanted to be all AP-ish, we could call this g of x, whatever, and we want g prime of x. We want the derivative of this. They kind of cancel out, but it's written weird. Okay, be cool. Rewrite it in a nice way. We need it from a constant to a variable. So what are we going to do before we derive? Flip it, and when we flip it, we need to. But is this going to an x or to a u? It's going to a u. We're not anti-deriving using u substitution. We're taking a derivative of an integral using f. And when we do, we're getting it properly oriented from a to u, from an initial condition to a final. Yeah, some of you are just your brains back into the pattern of what we're doing. Basically. Yeah. I would say FTC part 2. Our book's going to call it FTC part 1. We're going to say whatever, it's FTC. So g prime, take the derivative. This is an a to u. It's a negative, I suppose, a to u. Now it gets gross, because what do I need to do with that u? Plug it into all those t's. So we end up with 25x to the 4th, right? Squaring him. Minus 10x squared plus 9 all over 125 x to the 6th plus 6. Are we all tracking? F, I did all along. Right? So f of u times who prime? U can be all sorts of different things. Be careful. But in this context, we're talking about a to u. We have to legally get it in the form that we need.
Split it up.
Anywhere you want. Where do you want to split it up? 0? Sure. 5? Sure. 2? Sure. Does it matter where you split it up? Did this have any impact on the answer? No. Okay, so where do you want to split it up? Pick a number. Sure. So going through what Justin is doing mental math style, we could go ahead and do from sine to 0, and then from 0 to cosine. That's the legal way of, what was that weird word yesterday? Additivity, the additivity rule. However, why did Justin say flip it? I need a to u. So we're going to go ahead and flip this. Even though it is technically right, we now need to go ahead and make it negative 0 to sine of x. Remember, what's the point? Get dy dx. Take the derivative of this integral. So what do we have for the first expression? F of u. Don't get tricked by the trig notation. We know sine of x quantity squared is sine squared of x, right? But why is there a times? U prime. Who's u prime? Cosine x. Plus, don't get tricked by the trig notation, cosine squared of x times negative sine. Yeah. I mean, I guess we could pull out like a sine cosine, but difference between AB and BC. They're going to get back their chapter 2A tests. So many should have stuck it to the man, especially on their chain rule derivative. So sad.
Oh wait, but no, it was like 1A.
But your book also goes almost twice as fast. Like, I mean the chapters, so remember last year I split up, well, you might not. There was chapter 2A and 2B. Our book would have called it 2 and 3. Does that make sense? So, yeah.
They're on chapter 2.
Yeah, keeps them humble. Keeps them humble. Keeps you guys proud. I'm not sure if that's good or not. But then I throw some piecewise functions or absolute values at you, or maybe some... Now what? Oh, you're making a function. Okay, what do we got?
I'm not really sure. Oh wait, so it's the integral? Because they gave you the derivatives?
Yeah. And then they give you the minus. Alright, I think it's fine. It's just nice. No, that's fine.
You could do it that way. You could do that.
Where is it? Where does it say that?
Oh no.
No.
Where?
Like you could have had the u go and get plugged in for the derivative, right? You could have. Maggie saw the 5x. It could have been the u, right?
Okay, so
But then you would have had the u prime, and so you would have needed the 1/5. Or you could just have it be x and have that be 5x. You could do that too. See what I mean? That would probably make it a little easier as far as not needing to do u sub. See, we could have just written it. That's okay, because then the x gets plugged in for the derivative, right? Wait, why did I make it 7? Remember how I was telling you how I made the function and this could be the initial? So maybe the initial point is 7? Wait a minute, hold on, but I need a plus c. How do I... Wait, did you see me when I was setting it up on the page before? Remember? Integration is net change. That's really just I'm just going to make it y. Yeah. It'd be antiderivative minus initial because it's f of b minus f of a. So this c, if we were actually talking about the meaning of the accumulator function, technically this wouldn't just be called a c. Technically this would be y of 7. We haven't specifically done a lot with integration as net change, but ultimately this is using the antiderivative idea from section 6.3 that some of you guys need to finish up the homework on. But the accumulator function gets the original function, or I should say the antiderivative function minus the initial. So that's where we would plug in the negative 2. Oh, but what happens when we move it to the other side? Yeah, it's not going to be. Minus a negative is plus, so it's going to be a minus, right? Nope, minus a negative is a plus, and then we minus. So ultimately, if you make this the initial x, we can make this the initial y. And then we get to integration as net change as a result of kind of the relationship. But no, it's not this section. We've barely even anti-derived yet. Good. Take a second. I just call it the antiderivative part because we just talked about how last year's book and this year's book numbers it differently. It's difficult to overestimate the power of the equation. It says that every continuous function f is a derivative of some other function, namely the accumulator function. It says that every continuous function has an antiderivative. Equation deserves to be called the fundamental theorem of calculus. This equation is surely the one. It ties together the relationship between integration and differentiation. And it's able to make a blanket statement because of a lot of math behind it as far as characteristics of every continuous function. Anyway, I thought that was a cool way of wording it. Once again, I know our book is quirky, I know it's weird, but conceptually, it's quite deep, which is nice at times. The evaluation part. So the antiderivative part has to do with d dx of the integral. However, the evaluation part has to do with, so if we need to find the integral from a to b of a function f of x dx, we just do antiderivative b minus antiderivative a? Yes. Have you guys already been using this a little bit this year? Yes. Maybe cheating a little bit based on what they expected you to do? Yes. But are we okay? Yes. I think so. But I love that section 6.4 started off with going from a constant to a variable, which builds to an antiderivative. And now we're specifying going from a constant to a constant. Wasn't this what? No, section 1 was Riemann sums. And geometry? No, geometry was section 6.2. Section 6.3. I don't think it got very difficult, did it? That was pretty basic. 6.2 was geometry. Like I showed you trig sub because you guys have already taken calculus. Trig sub was not at all what you were supposed to be doing. You're supposed to be drawing a semicircle and saying, yay, geometry. I'm blanking on 6.3. 6.3 was MVT for integration. Well, that's what if you guys look at the chapter 6 is the definite integral. So it's tearing apart different facets. But we introduced integration using Riemann sums, which are technically an approximation of definite integrals. So technically indefinite comes from the All right, guys, finish up 6.3 for tomorrow. Don't worry, we have another day for 6.4. Go team? Go team.